Hello, my name is Matthew Kozubov, and I have a fun video for you all today. So in today's video, I would like to show you a simple method for controlling for confounding variables. This lesson is designed for data science students that know what a confounding variable is and want to intuitively understand the phrase controlling for confounding variables without rigorous definitions or detailed implementations. The video will contain three main sections, and in the first section, I will present how confounding comes up in something called single-cell RNA sequencing analysis. After understanding that context, we will see the intuition behind what controlling for a confounding variable actually is. And finally, I will finish with a brief showcase of how you can implement our intuition as an algorithm in the programming language R. So first, here's my concrete example of how confounding comes up in single-cell analysis. So let us imagine that we are a researcher studying cells. Each cell is full of genes, and we have developed a method to count each gene. So using our method, we have counted that there are 3 red genes, 1 orange gene, and 6 blue genes in this one cell. Now, we have generalized this technology to sequence thousands of cells and count thousands of genes. We can put the results into a matrix, as shown here, with cells as rows and genes as columns. This analysis is called single-cell analysis, and it produces an enormous amount of data. So much data that the first challenge is actually picking which genes to focus on. It has been shown that genes with high standard deviations contain more useful information, so let's see which genes have the highest standard deviation. It would be very simple to write a program that goes column by column by column and calculate the standard deviation of each gene in the data set. Then we would just sort this matrix, or this vector, and select the top variable genes. Unfortunately, we would be neglecting to model an interesting relationship that exists between the gene's mean expression and its standard deviation. Here, I'm showing a figure where each dot is a gene. The x-axis is the gene's mean expression level, and the y-axis is the gene's standard deviation. If the two measurements had no relationship, we would expect a random smattering of points, but that's not the case here. Simply sorting from the top to the bottom would actually ignore this relationship and could lead us to miss interesting genes and lose out on interesting results. And this leads me to the most important slide of this slide deck. Right now we are asking the fundamental question, how can we remove the effect of mean gene expression from our variance measurement? And the answer is super simple, we make a best guess. What is the best guess and how does this help us? Well, let us say that I fit a line to my data. This is my best guess. Now, I have some sort of frame of reference to see what a gene's variance should look like for a given mean expression level. If a gene shows much higher variance than I expect, it sets off alarm bells and we should make note of it. But fitting the line isn't the simplest way to do this. Let's look at a much more intuitive example of how we can make this best guess. The method I wanted to show you all today is called binning, and it's a super simple process. Step 1. We take the graph and bin it along the mean gene values. Then, in each bin, we would calculate the average and the standard deviation of the y-axis. Now, within each bin, we compare each gene's variance to these best guesses we have made. And this is the core concept for how we will remove the effect of mean gene expression from the gene's variance measurements. Now, let's hop over to R and see how to implement it. So, we start off by actually reading in our data set, and we can see that the rows are cells and the columns are genes. Plotting the variance versus the mean expression shows us the plot from my presentation. And now, I did binning a little bit differently than I presented. Rather than binning in equally spaced segments, I decided to bin by quantile. And we can see that the data is right skewed. And for visualization purposes, I put the x-axis on the log scale to see the bins a bit more clearly. But calculating our best guesses within each bin give us this graph, and standardizing the values lead us to this final plot. So in this final figure, we can see that the relationship between the variance and the mean seems to have been partially corrected for when we plot the standardized variance here on the right. It looks a lot more like a smattering of points, and if we look from top to bottom, we have successfully brought some of the lowly expressed genes towards the top. And that actually brings me to the end of my video. Today, we learned what controlling for confounding variables really is, and it's as simple as making a best guess. If you have any questions, please leave them in the comments below. I would love to answer them. Thank you for watching, and I'll see you in the next one. Bye for now.